4 billion years ago, Earth emerged as a cradle of life in an indifferent universe. This blue planet, a single speck amidst cosmic void, bore witness to the incredible journey of living matter. But the story of life may stretch far beyond our humble world, perhaps even back to the very dawn of time. The mysteries surrounding the origins of life, the apparent rapidity with which it bloomed on Earth, and the question of whether we are truly alone, all converge to paint a picture both wondrous and deeply puzzling. Imagine the early Earth, a world shaped by violence and fire, where meteoric bombardments and volcanic eruptions raged across continents barely cooled from their primordial birth. Oceans gathered, steaming and frothing, under a sky choked with noxious gases. Yet in this apparent chaos, something magical happened. Life emerged, seemingly as soon as conditions allowed. Microbial cells appeared, tiny architects of biology, transforming inert rock and watery chaos into a teeming landscape. This near instantaneous blossoming of life, as soon as the planet was stable enough to host it, is a paradox that challenges our understanding. The basic components that define life, the genome and the proteins that implement its instructions, are tangled in an intricate dance of mutual dependence. A genome requires proteins to read it. Proteins, in turn, are specified by the genome. It's a conundrum not unlike the chicken and the egg, each relying on the other's pre-existence. Early Earth had immense time on its side, but the leap from lifeless chemicals to complex replicating cells is so steep that, even in the billions of years available, it almost seems insufficient. That life managed to cross this threshold so quickly suggests either a hidden efficiency in chemistry, or, perhaps, a cosmic origin for life's seed stock lying in wait for the right planetary nursery. Scientists have long tried to rebuild the chain of events that led from molecule to microbe. Theories abound, from self-assembling RNA molecules in primordial pools to hydrothermal vents driving exotic chemistries. But each approach runs into the same daunting odds. Constructing such vast molecular machinery by mere chance seems unlikely in just a few 100 million years. How did matter without memory or metabolism craft the blueprints for all future complexity? Perhaps we are thinking too narrowly. Focusing solely on Earth risks missing the universal context. When we measure the rate at which genetic complexity has grown over time, an intriguing pattern emerges. If genome size doubles roughly every 350 million years, as some analyses propose, and if we roll the clock backwards, we find ourselves facing a provocative implication. The genesis of the simplest protogenomes appears to fall not within Earth's lifetime, but nearly 10 billion years ago. That points to an origin predating even the solar system, a chronology suggesting that life may have begun elsewhere, its seeds drifting through space, only to bloom anew on worlds like ours. This is the idea of panspermia, that the seeds of life are not unique to Earth, but are instead a cosmic inheritance, scattered across the stars in meteorites, dust, and comets. Microorganisms, or the chemical instructions required to birth them, could survive eons in interstellar space, slumbering in the cold void until meeting a world with the right ingredients and a little warmth. On such a world, perhaps Earth, perhaps others, dormant life could awaken and adapt as if rising from a long cosmic sleep. But could life truly be that old? The young universe following the Big Bang was hot, dense, and unruly. Yet numbers suggest that between 10 and 17 million years after creation, the average temperature across the entire universe cooled to a range suitable for liquid water, between 0 and 100 degrees Celsius. For a brief span, cosmological conditions were right, everywhere, for the formation of complex chemistry and perhaps for life itself. Picture a universe heated not by sunlight, but by the fading afterglow of creation, awash in newly born stars, their supernovae forging carbon, oxygen, and nitrogen from primordial hydrogen and helium. In the dice rolls of chemistry, perhaps somewhere the first spark of self-replicating matter caught hold. Even if such ancient life bore little resemblance, biochemically or physically, to what we recognize today, it is conceivable that some form of protobiological evolution began. Life may not require water alone. Other liquid solvents, such as methane or ammonia, could serve on worlds colder than Earth. mirroring environments present in the ancient cosmos and on certain moons today. Thus, early life may have been exotic, spread across planets, moons, and the surfaces of cosmic dust grains, only to evolve and diversify over billions of years into a tapestry that now includes us. The poetic concept of the green universe comes alive here, a cosmos that in its infancy teemed with potential for life. Not a barren vacuum, but a nurturing cradle, briefly fertile wherever conditions aligned. This nurturing phase did not last. As expansion continued, temperatures fell, and worlds without internal heat froze. Yet the seeds may have survived, carried inside primitive celestial bodies, lying dormant for millions or billions of years until fate delivered them onto newborn, habitable worlds. Thus, the rapid emergence of life on Earth becomes less mysterious. Our planet may have been pre-primed by a cosmic legacy stretching across ages. What then does this mean for our search for life beyond Earth? The implications are profound. If life's origins reach so far back, and if the law of increasing genomic complexity is real, then life should be common. Mars, with evidence of ancient rivers and lakes, may once have harbored its own share of this primordial inheritance. Saturn's moon Enceladus, spraying water-rich geysers into space, and Jupiter's moon Europa, with its subsurface oceans, are enticing as possible hosts. Even more tantalizing, Titan's liquid methane seas resemble the conditions of the early universe, suggesting that life's adaptability might far exceed anything we have imagined. If somewhere on Mars or Titan we discover even the faintest traces of biology, a fossil, a microbe, a chemical signature, it would strongly suggest that life is not the fluke of Earth, but an inevitability of cosmic evolution. Such a discovery would transform our conception of the universe, revealing not a universe empty and indifferent, but one alive in ways yet unimagined. It would make us, all living things, descendants of a shared genesis, a testament to interconnectedness across unimaginable stretches of space and time. No signals have yet reached us from thinking beings beyond our world. Perhaps intelligence is rare, or perhaps the silence is only temporary. The brief pause before other civilizations, following their own evolutionary journeys, lift their gaze to the stars and begin to wonder, as we have, about their place in the cosmos. Yet even now, as we send probes to icy moons and sift Martian soil, the possibility persists that the answer to life's greatest riddle lies within our reach. If the seeds of life are indeed everywhere, then each planet, moon, and drifting asteroid is a potential cradle. And if we share a cosmic heritage, we are all, in some sense, a single family, bound not by borders or biology, but by the universal drive to live, adapt, and explore. The green dawn of the cosmos may be distant in time, but its echoes still shape our fate. As we press farther into the darkness, the promise remains. Somewhere out there, life still waits to be found. We need only persist in our quest to find it. Did you find our videos helpful? Please like and subscribe to our channel so we can be motivated to answer the questions that people are still wondering about.